Thank you so much. It's really I really appreciate the opportunity to come here. I've been enjoying my time in Chicago, even though I am a Pirate fan. You have to bear with me. But I do hope the Cubs have a great year and do get into the World Series. It would be wonderful for everybody. Today I'm going to talk about SPME and hopefully give you some insights on how we can optimize SPME. I'm going to briefly go over some basic theory. I understand a lot of you are already current users. So the beginning section I may actually go through relatively fast. Fiber selection, method optimization, applications, and a brief overview on quantification. And then look at some new products, SPME overcoated fibers, and then SPME, SPME, or for solvent desorption, either way you want to look at it, so it can be interfaced with HPLC. Basically, SPME is a solvent-free extraction technique. You can extract from a variety of matrices. It can extract from volatile to non-volatile analytes. It's an alternative to many other extraction techniques, or in many cases complementary with them. It can be directly interfaced with GC outlets without having to modify your GC. It's non-destructive to the sample. It's reusable, which makes it fairly cost expensive, and it's fast and easily automated. Basically, it consists of two components, a fiber assembly and a holder to control the fiber assembly. The fiber assembly consists of two pieces, an outer needle and an inner needle. And the inner needle has a coated fiber attached to the end of it, which can be retracted and exposed when the top color-coded hub is attached to the holder. This allows you to pierce samples and expose the fiber for septa and expose the fiber for sampling. So basically, you would insert the fiber, expose it to the sample or the sample headspace. After a given amount of time, the analytes migrate onto the fiber. You would retract the fiber, take it over to the GC inlet, pierce the septa, expose the fiber, the analytes from the heat of the injection port and the flow of the gas, push the analytes onto the column. And after a few minutes, the fiber is clean, it can be retracted, and the holder can be taken over to another sample and start the extraction process all over again. The thing about SPME is that it is a non-exhaustive extraction technique. It's an equilibrium method, and it is very matrix dependent and dependent upon the coating on the fiber. The fiber coatings usually consist of phases or polymers, excuse me, and these polymers may also contain particles such as silica, carbon, or porous polymers. If you look at the extraction time profile versus analyte response, you generally get this type of curve where you have a rapid uptake and eventually it begins to level off. At that point, you're at equilibrium, where the amount of analyte going into the fiber equals the amount of analyte going out of the fiber. This curve can vary. This would be more typical for a volatile compound. A semi-volatile, large semi-volatile compound may have a much flatter, slower curve. The amount of analyte extracted is dependent upon the distribution constant. And essentially that is the concentration of the analytes in the fiber versus the concentration of the analytes in solution. So SPME is more concentration dependent than it is volume dependent. Using a larger volume generally doesn't gain you any advantage compared to, because it's more concentration dependent. Now, when you're classifying the types of coatings, there are absorbent coatings and adsorbent coatings. Now, absorbent coatings are just simple polymers such as a GC type phase, PDMS, or polyethylene glycol, and they retain the components, the analytes, basically by the affinity of that analyte for that coating versus a matrix, and by the thickness of the coating. Those are the primary factors. They do not compete for sites, and generally these fibers have pretty good capacity, especially the thicker coatings. Now, the absorbent type of fibers have particles embedded into the phase that physically traps or interacts with the components. And that's either by the particles going into the pores, or the analytes going into the pores, or interacting with the surface area of the particles. There may be some competition for these sites, depending upon the affinity of the analytes for that surface interaction and how strong it's retained. And as a result, the fibers tend to have less capacity than the absorbent type fibers. Fibers can also be classified by either polarity and also by the thickness and type of coating. It's more, you need multiple thicknesses with absorption fibers, since it's more critical for that thickness in the retention of the components. Small volatile compounds, which move much faster, need a thicker coating to retain them, whereas large analytes are not going to desorb very well off of a thicker coating. As you can see, there are a couple of polar coatings for this. As far as adsorption goes, you can look at carboxyl and divinylbenzene as absorbents. And we call these bipolar because once the analyte gets into those pores, it's primarily retained. And we have one combination fiber, which I will talk about a little more detail later. Now, when selecting a fiber, I think the best way to do this is to look at the molecular weight range of the analytes. And this is a guideline of the molecular weight range for the various fiber coatings. This would probably be more of the optimum region. These can vary. It's not absolute, so but they can be used for guidelines. Carboxyl with small pores traps small analytes and can extract down to about 35. But once you get about 150, the analytes do not come off the fiber coating very well. And in fact, they come off so slowly that you don't see a distinct peak. Divinylbenzene has larger pores, so its molecular weight cutoff is about 50. And then when you get to the adsorbent fibers, it's strictly, again, the thickness, with 100 micron having a molecular weight cutoff around 70, and that going out to about a little over 300, where the 7 micron is around 140 and even higher than 500. So the absorbent fibers, the coating thickness affects the analyte selectivity. Extraction time, it takes longer to reach equilibrium with a thicker coating. Sample capacity is better with a thicker coating, but the carryover and incomplete desorption are an issue with a thicker coating. This is shows the aromatics from 1 ring out to 6 rings. You can see the 100 micron does better for these for C1 up to C5 rings, or whereas it has problem desorbing the C or the 6 ring PAHs, where the 7 micron does very well at desorbing these and poorly retains the smaller molecules. The 30 micron is a nice compromise.
How do you get the high recoveries of 140%?
Yeah, that's sometimes, you know, that I'm not really sure how. In many cases, when you're, this is relative to the Chrycine response, so its response was higher than the Chrycine for these. That's what it's, I should have said that at the beginning, I apologize. The polar coatings, of course, determine selectivity. Polar coatings will extract polar analytes better. And there are 2 types that we have right now. Polyethylene glycol, which is the most polar fiber, and the polyacrylate, which is moderately polar. This slide shows the effect where the polar analytes are extracted very nicely by the PEG fiber and moderately well by the polyethylene glycol, where the PDMS is 3 orders of magnitude less for paranitroaniline than the PEG fiber. The pyrene with its double bonds is actually extracted well by all the fibers, because polar does have some affinity for double bonded molecules with the aromatics. But when you look at undecane, a linear hydrocarbon, you can see the PDMS is much better, and where the PEG tends to repel hydrocarbons, so you can see the selectivity advantage that it has if you're trying to extract polar analytes that also contain some non-polar analytes. Effects of porosity, it's better for trace level analysis. The pores retain the analytes more tightly. You vary the pore size improves selectivity. An analyte with that's about 10 angstroms in diameter can retain a 5 angstrom size molecule. Divinyl benzene is primarily larger pores, where carboxyl is a mixture of all 3, but has a high degree of microporosity. This shows a electron micrographs of the cross-section of a PDMS DVB fiber. This is the core, the fused silica core, and this is a stable flex fiber, so you see this thin coating of plastic around that fused silica core, and then you have the absorbent embedded in PDMS around the fiber. This one at 3000 magnification shows the close-up particles of carboxyl 1006, and you can see the PDMS binding it to the fiber. The PDMS really has no effect on the absorption property relative to the strength of the carboxyl. And that can be seen very easily in this slide, where the carboxyl, shown in black, extracts nearly 200 to 300 times more than the 100 micron PDMS fiber. And these are actual area counts of the peaks. And so that shows the effect that the porosity has on retaining these smaller analytes. The larger pores of divinyl benzene in yellow is significantly less, because the pores are not meant to retain, but they do retain a little bit of these smaller analytes. Conversely, when you go to large molecules, the carboxyl has trouble desorbing, especially the planar Chrycine. It's 3 orders of magnitude less than the polyacrylate fiber. The polyacrylate fiber really likes aromatic compounds, so it's a pretty good fiber for these type of analytes. So how would we have an adsorbent absorbent type fiber that would also extract a wide molecular weight range. We took some lessons from Purge Trap and decided to coat carboxyl PDMS around the core of the fiber, and then a layer of PDMS DVB around the carboxyl layer. So larger analytes are going to be trapped in the DVB layer. The smaller ones are going to pass through and go into the carboxyl layer. So what you have now is a more universal fiber. In fact, this has become by far our largest selling fiber coating because of the wide molecular weight range that it can extract and because of the trace level of sensitivity that it can get. The recommendations for using absorbent fibers, again, we want to only use these for trace level analysis and use by headspace if possible. Keep the extraction time short, no longer than 30 minutes. Keep the injection port hot, and this is very important. You want to be near the max temp of the fibers, especially the divinylbenzene. That's a limiting factor of 270. Keep the fiber up on at that zone. It will help release the analytes much more efficiently and clean the fiber out better. You also want to clean the fiber if it's been sitting around because it will pick up the chemicals in the lab. Now let's shift bases a little bit and look at method optimization. How can we increase that distribution constant? Of course, the fiber coating is very important. The sampling technique, whether you use Aversion or Headspace, you can modify your sample by the addition of salt and pH adjustments, and some instrument modifications and the use of agitation can all play a major role. Headspace versus direct immersion. Of course, that's dependent upon the volatility of the sample. It must have at least some vapor pressure to be able to do headspace extraction. Extraction is faster in the headspace than it is by immersion, because the analytes will move faster through air than they will through a liquid. And of course, it's matrix dependent. We can't immerse a fiber into a solid. And it does play a role in selectivity. You can fine tune which analytes you want to extract and exclude. SPME headspace extraction has two equilibriums. You have an equilibrium between the sample and the headspace, and an equilibrium between the headspace and the fiber. So as analytes go into the fiber, more come up out of the sample into the headspace. And if you're using particularly a thick fiber coating or an absorbent type fiber, you can get a pumping effect so that you get a lot of concentration of analytes onto the fiber. It's much better for semi-volatiles than traditional headspace because of this effect. And the nice thing is you don't have to heat your sample real hot. 40 to 65 degrees is usually adequate. Now the effects of pH and salt are shown in this slide. In many cases, if you're extracting polar analytes, you want to add 25 to 30% sodium chloride. This increases the ionic strength and usually increases analyte uptake. I say usually. For some polar analytes, it may actually be for non-polar analytes, it could be detrimental because it may force them out onto the walls of the glass valve. When you're extracting bases, you want to be 2 units above the pKa if possible. That's not always possible, but it puts them in the non-ionized mode. The same with acids. You want to be 2 units below the pKa for acidic compounds. Non-ionized analytes are less soluble and more volatile, which makes them easier to extract. Extraction of PAHs is shown in this spec, and you can see that when we at a neutral pH without any salt, we get very poor extraction efficiency of many of the analytes. Adjusting the pH increases it. Adding salt is more effective than just pH, but when you combine them both together, you see the effect of about 100 times to even 1,000 times more uptake than without those adjustments. The only modification we recommend for an inlet is to use a 0.75 millimeter liner. This reduces band broadening, increases the linear velocity of the sample through the of the gas through the liner, and pushes the sample onto the column much more readily. Now you'll also want to couple this with a thick film column if you're doing a volatile analysis. In most cases, you won't need to use cryofocusing. Agitation is essential, especially for larger analytes. It reduces extraction time. It increases precision. But it's important that the agitation be consistent. It's not necessary for volatile compounds, but most of the time I still use it. And beware of sonication, because you may increase the temperature of the sample, which could change the recovery. Let's look at some Headspace applications. Milk flavors, off flavors. The aldehydes are formed by the formation or cleaving of double bonds when UV interacts with the fats, and that forms, the cleaved product is oxidized and forms aldehydes such as pentanal and hexanal. And you can see just after 1 hour of exposure to sunlight that the two pentanals and dimethyl sulfide, which occurs from the cleaving of sulfur-containing amino acids, are formed, and these have off odors and flavors that some people can pick up very easily. This is an extreme case of this. Somebody left a bag of chips in the lab that they bought for analysis. They left the company. I found them 2 years later. You can see the high degree of rancidity. Not only did hexanal, a lot of hexanal formed, it was further oxidized into hexanoic acid. You see that with heptanoic acid also. Extremely large peak. You compare that to a fresh bag of chips, but even then you're starting to see a little bit of hexanal. It's almost impossible not to get some cleavage of these double bonds. This profile shows roasted coffee, and most of these compounds out here are pyrazines and furans. We got a bunch of interesting smaller volatile compounds that are present in coffee. And you can see there are some ketones, and you also see a little bit of these hexanal and disulfides formed. But most of them are pyrazines, which occurs from roasting of the coffee, reducing sugar and the amino acid. The analysis of honey, we're just showing this to show how nicely it picks up these volatiles out of a SERPy type of matrix. And this one shows a difference between the different types of flowers, primarily C9 components compared to acacia honey. So it's a good way to tell if a label claimed it was 100% acacia and you saw a lot of these components in there, then you realize it probably isn't. Peppermint oil. The reason I put this slide up here was to That menthol boils at 100 and boiling points 212 degrees, and yet it extracts very nicely at 45 degrees with a simple 5-minute extraction. We got very nice peak of the menthol isomers. Volatiles in white wine. Again, we're trying to emphasize the fact that even in the presence of 12% ethanol, we were still able to get these components that are probably present in ppb or ppm levels. Even compounds like acetic acid and sulfur dioxide are shown in this chromatogram. In this case, we used just a straight carboxyl. The other two with coffee was a DBB carboxyl fiber. Same thing with beer. Pick up carbon dioxide. I did not degas the beer before analysis. And you can see we got a lot of the, again, similar components that are in the wine from fermentation, but obviously different amounts. And again, the carboxyl fiber was used. Looking at bourbon samples, I wanted to show this one because the effective salt, I added about 15% salt, which is about saturation. You can see that there's really not much different between the chromatograms. In fact, these ethylated fatty acids actually decrease with the presence of the salt, and that may be due to them plating out on the valve walls. So in this case, we decided to do the analysis of these distilled beverages without salt. You can see the difference between the bourbon and the whiskey, which is filtered through charcoal, and that removes many of these longer chain esters. This is a bourbon-based liquor, which had some fruit flavoring added to it. You can see a lot of components that are common in the with fruit flavors, but you still see some of the bourbon components present. This was just for fun. I threw in a gin sample just to show the terpenes, the monoterpenes, and the diterpenes. But it also has a few of these distillation or components from fermentation in there. If you cut up an apple and try to do an analysis, you're going to immediately, the apple's going to oxidize, and you're not going to get the true flavor components. In this case, they had a jar purging with nitrogen. They put the apple, cut it, put it in the jar, and then passed the gas stream over the fiber, and you could see it picked up these flavor components very nicely. Comparing of residual solvents, we just got some ibuprofen tablets. One was a generic brand, and the other one was a brand name, and you could see the difference in the solvent profiles of the pills. I'll briefly go into how to quantify samples. One of the things you have to do, most of the time you just spike your standards into the same type of matrix that you're analyzing, usually water. The matrix between the standards and the samples must be similar. You want to generate a calibration curve. Use internal standards that are similar to the analytes or behave similarly. And all the extraction parameters must be consistent, and that's easier to attain with automation. This is an example of odor-causing components. This is these are components that form when blue-green algae grows on in reservoirs or ponds. The algae off-gases these musty-like components. And the human nose can often pick these up down to 5 parts per trillion. My wife particularly is very sensitive to these. It can also be absorbed, these components can be absorbed into fish that grow in the, that are being raised in the ponds, especially a whitefish like tilapia or catfish, which are often raised in farm-raised ponds. But you can see that using the DVB carboxyl fiber, we also have a 2-centimeter version of that, and that was designed particularly for this analysis, so we could get down to 2 parts per trillion. You can see we got a very nice calibration curve. This is relative to trichloroanisole, which is another odor agent that's very sensitive, and which usually forms in wine. And you can see very good linearity on these from 1 part to 10 parts per trillion, and our y-intercept is very low. The analysis of peanut butter. This is another one where the Maillard reaction and the formation of pyrazines, primarily from 9 to on out. And we also see some of the off-flavor components here in the beginning. Carbon disulfide, the aldehydes and sulfur components. Because peanut butter does have a lot of oil in it. And then we look at the pyrazines, which are the flavoring compounds from the roasting. Now, how would you analyze something, a food component, when you don't have a matrix that doesn't have those components in that's similar? One of the ways to do this is sample addition, where you would take your sample and divide it into 2 vials. You would try to get about the same amount of weight in each one. You can adjust that. And you would spike one of the samples with a known amount of the particular pyrazines that you wanted to analyze. You sample both identically, and then subtract the unspiked from the spiked, and that gives you the area counts for the amount that you spiked into it. Once you know that amount in relation to the area counts, you can do a direct proportion to determine how much was in the original sample. And for these 4 pyrazines, you can see the results with 2,5-dimethylpyrazine being the essence of peanut butter. You can see it's a pretty high concentration level of that. The notice of 2-methylpyrazine is at 158. Another way of doing that is to do multiple vials of the same sample and spike at different levels with the components of interest. And then you would draw your calibration curve, response versus concentration. And at the y-intercept, this is the amount that was in your original sample. So, and we calculated that, dividing that number by the slope of the line, and you can see we get 154.4 with multiple point addition versus 158. So essentially the same. Some applications by direct immersion. These are herbicides at 2 parts per billion. They're fairly polar, moderately basic herbicides. These are breakdown products where the isopropyl and the ethyl groups have been removed, making them even more polar. You can see we're still extracting these in the presence with using the polar PEG fiber and the addition of salt to the water. Now this resveratrol is a antioxidant that's common in red wine. But it's a non-volatile component. It's not going to be, you're not going to be able to analyze that by GC unless you derivatize it. So we came up with a non-fiber derivatization technique. In this case, you could take the red wine and extract it with the polyacrylate fiber, and then you expose that fiber to a derivatizer reagent for 20 minutes, Cylon BFT, and then when it's put in the injection port at a high temperature, the reaction between the the derivatizing reagent, and the resveratrol occurs and you get a derivatized peaks. You can see that in this slide. You see the 3 hydroxy groups are silanized, and you get 2 isomers, a trans and a cis, and the trans is the more active of the 2. Again, we see the calibration curve. Instead of spiking the wine, we just spiked 12% ethanol to get the calibration curve. It seemed to work pretty well. We looked at the trans of unspiked red wine, came out with about 22, and the recovery of the spiked amount was of 100 micrograms, came out about 134. With the 22 that was in there to begin with, that's pretty close to what you should be, and we probably had some background, a little bit of background that was contributing to it. You can see the 2 slides here of the spiked and unspiked. Now I'd like to shift bases a little bit to some new products that we were using for SPME. And look at the overcoated fibers. We wanted to be able to use SPME in more complex matrices, primarily food matrices. Compounds such as sugars and other non-volatiles, dyes, tend to stick particularly to the absorbent, the divinyl benzene component, which is going to be exposed at the surface. So we wanted to figure out a way, how can we keep this matrix from binding so much with the component, with the fiber, and still allow the components of interest to pass through. So we put on a coating of a proprietary PDMS, which is a little more rigid, and that serves as a barrier to the matrix, and the components tend not to stick as much with this PDMS layer. The analytes migrate through the PDMS coating and are retained by the pores and the surface area of the absorbent. The fibers are definitely more durable, and the overcoating does reduce matrix competition with the analytes. So it proved to be fairly effective. This shows the more translucent appearance from the PDMS overcoating over the fiber versus the non-overcoated PDMS DVB fiber. The nice thing is we dip coat the final fiber. So what that does, it seals the end of the fiber where it is normally cut. And it also seals where the fiber is attached to the needle. So you get 2 effects of sealing the matrix from getting in. Where the fiber is cut, you can see we can get fine cracks and openings where the matrix can't get into the fiber coating. It can cause a little bit of chipping around the very tip of the fiber coating. Where with the overcoating, it does protect that end. The neat thing, again, you can see the core, the stable flex, and then the adsorbent around. We looked at a bunch of semi-volatile components, primarily pesticides and some nitroaromatics. So I put these in there because they are much less molecular weight. Now, the PDMS DVB fiber is not a highly polar fiber, so once you get much below a log P of 1.5, you're not going to extract analytes real well, but it does it extracts these moderately polar analytes very nicely. So why extract out of grape juice? because it has a very high sugar content, in this case 157 milligrams per mil, the dark color can be easily detected. It has a lot of other non-volatile components in it. And we try to use we used a brand name to try to retain consistency between the multiple samples. In this case, we put 7 mLs into a vial, immersed the fiber. That's where the reason we picked the components we did is because they have very little volatility. So you have to immerse the fiber. And then after extraction, you want to rinse the fiber in water. Now we did all this using the auto samplers, and which is really essential for this type. And then we did a desorption. And in some cases, in this case, we didn't do a post-rinse, but in some other later applications, we did do another post-cleaning of the fiber after desorption. This compares the first and 20th extraction, and this is the percent decrease between the first and 20th extraction. For the non-overcoated PDMS, the standard fiber, after 20 extractions out of grape juice, we get probably an average of about 40% loss of analyte across the board. Whereas with the overcoated, we have about a 10% loss of analyte on average. This shows that what we did, we extracted 20 samples at a time, inspected the fiber, and then extracted another 20 samples with a fresh set of samples. So we spiked 20 every time. And so what you see is this pattern of decrease, and then you kind of get a little bit of a lift because the pesticide does bind to the matrix to some degree also. That's why over time it even drops further. But these were normalized to the first extraction, and so this is relative. So with this, there's essentially an 80% loss after 40 extractions, where there's only about a 20% loss with the overcoated fiber. So it does about double the lifespan of the fiber. You can see some of the buildup of the carbon on the non-overcoated fiber, where the overcoated one is much cleaner. So what we found out that it does help to some degree, but it's not a cure-all answer. We've looked at other matrices, including baby food, spaghetti sauce. We found that you can reduce matrix interference by heating the samples. Usually when you do direct immersion, you don't heat the samples, but we found that heating at 50 degrees greatly improves that recovery. You want to make sure your sample is thoroughly mixed, especially if you're spiking standards into it. You want to make sure it's thoroughly mixed and thoroughly dissolved in there. Compounds with real high log P values, such as DDT and other chlorinated pesticides, tend to bind even more harshly to the matrix. So it can be quantifiable. It does produce cleaner chromatograms. We've compared it to catchers, and there are some advantages of it, but it's certainly not, it does have its limitations. But it can help you if you're looking for specific compounds. Now the last thing I wanted to talk about are the introduction of SPME fibers for solvent desorption, primarily designed for biological analysis. Excuse me, I pushed the wrong button. There's been a growing tendency to look at microextraction techniques, and to do this, we needed to have a solid phase microextraction fiber that was viable in a matrix that would repel large analytes such as phospholipids, and proteins. And we've been able to do this with the coating of bonding silica into a proprietary binder. It does not swell in any solvent, and it's very rugged and durable. But the primary concern with BioSPME is that you can't do multiple analysis with one fiber. Most likely it has to be single use. So we had to come up with designs that were much less costly to produce and allow the person to be able to do single extractions. So we came up with biocompatible probes. As you can see, this is a metal fiber that has been stripped. It's about 7 centimeters long. It has a hub attached to one end. It's put in a 22 gauge hypodermic needle and sealed with caulking. And that alone can act like a holder and fiber all in one. So you can put this into samples and extract out of vials. You don't need to seal them since we're working primarily with non-volatile analytes. But it can also be put into difficult matrices such as living systems, animals, plants, cell cultures. And in some cases, we can get multiple data points. After you would extract the samples, you would take them over and put them into a small amount of solvent, and solvent desorb them. And then you would take those vials that contain the analytes and put them into your HPLC for analysis. This is an example where it was used in a pharmacokinetic study where they give a mouse a drug and over a 24-hour time period monitor the amount of loss of the drug versus time. And the issue with that is that they have to kill multiple mice because they remove 2 mLs of blood from the mouse, which kills it, and then they do the analysis. And to do this one study, they usually take anywhere from 8 to 12 points, and you like to have 3 replicates at each point. So that could involve up to 36 mice. And if you're using transgenic mice, that can be very expensive, let alone the ethics of euthanizing so many of the rats or mouse. And so in this case, we create a shunt device. The blood is passed through the shunt back into the mouse. The fiber is then exposed in the shunt. Or you can clip the tail of the rat and then insert the fiber into the tail. And what that means is one mouse can be used to extract all the time points. So you're not even sacrificing the mouse, and it also allows you to sample with one metabolism. The other way we're looking at these analysis is to put the fiber into pipette tips, insert them into, and then look at 96 well plate design where we could extract 96 samples at one time with 96 fibers. This would, even if it takes a half an hour to an hour to do the extraction, you've made 96 extractions. You would then pick up the tray and carry it over to another tray containing solvent, put the fibers into the tray, and then solvent desorb them. Then again, the tray can be put into an HPLC autosampler and the samples run. So it's a fast way of doing multiple extractions, and it should be, in the long run, fairly cost effective. And we've looked at this with urine and with plasma. In many cases, in this case, we're looking at a silica with a mixed mode phase, which is C18 and a strong cation exchange. We're looking at the extraction of amphetamine type compounds or bath salts, synthetic amphetamines. Generally, when they do an analysis, often they just precipitate the protein and make a direct injection into the HPLC. And so we compared that to an SPME extraction. You can see we got about 2 times the increase in response. It's further enhanced by the fact that the BioSPME repels phospholipids. You can see that monitoring for phospholipids, there is much less shown with the fiber versus that the subsequent, those where the protein was precipitated. You still have a lot of phospholipids remaining in the supernate. We looked at drugs of abuse from urine. This was a study which where we worked with a Prosolia and looking at some of these compounds out of that were present in urine that were previously monitored by ELISA. To do this, we soak the fibers for 10 minutes in methanol and water, and then extract the samples and then desorb them in methanol with a little bit of ammonium formate. Now, as I said, these samples were previously screened by ELISA. You can see some are post-mortem by the high concentration of the drugs present, but you can see that the fiber was very good at extracting over a wide concentration range for all these fibers. And how was this done? This wasn't done by solvent desorption. The fibers after extraction were put into a direct interface with an MS-MS. As you can see, the fibers were mounted, and then the spray, electrospray, nebulized electrospray was sprayed over the fiber, and the ions are then go directly into the mass spec. So it's, and what you get are timed profiles where you see these peaks forming. They're called chronograms, and you just calculate the total area. You use exact masses then to identify the drugs of interest. And you can get some very nice calibration curves. These are, again, relative to the deuterated forms of each drug. You can get a nice linearity over the concentration. So what you get is a way to sample. It takes 10 minutes to 20 minutes to extract the samples. You extracted 96 at a time. It takes 1 minute to do the analysis. And the nice thing with these is you can resample the fiber again over time. And we found that the drugs stay very stable on the fiber. In some cases, they went back and reanalyzed the fiber with the direct interface, and were able to get the same responses after a couple of weeks on the fiber. The other way to do it is with a dart, which uses thermal heated gas, and then it's directly interfaced into the mass spec. In this case, you vary the temperature of the gas going over the fiber, and depending on the compound, you find out the temperature that is best. But again, all these techniques on these direct interfaces are when you're looking for known compounds or for a series of compounds that you're scanning for, because direct exact mass is a requirement for the analysis. Okay, so a lot of information I gave you. I appreciate your time that you have given to me, and I'd like to open it up to some questions if you like to. If you like that, I'm willing to stay afterwards if you want to talk at all about what you're doing. If you have specific questions, you can always email me. You might want to write down that contact address. I will respond to you, and I'd be glad to work with you or my colleagues at the in the lab. We do have an applications group that we sometimes are willing to do outside samples. So I appreciate your time, and anything questions you may have, I'm open to them. Thank you.